Question 10 in the VCAA 2018 chemistry exam. Bioethanol is produced from the fermentation of glucose. According to the equation below, this is our fermentation equation. The mass of ethanol obtained when this much carbon dioxide is produced is what? Well, if we got carbon dioxide, this is a pretty much straightforward mass-to-mass stoich problem. So therefore, you're going to find number of moles of carbon dioxide equals mass over molar mass. You're going to ratio it, which is 1 to 1. And then you're going to work out your mass of ethanol, which will be equal to number of moles times molar mass. So let's first of all work out our number of moles of carbon dioxide. It is going to be 5.68 divided by 44, because I know that's my molar mass of carbon dioxide. You should start to understand some of the molar masses, the regular ones that you see, and that will help you in your timing here. Also, mass of ethanol is another one you'll probably get to know pretty well. It's 46. So therefore, that's going to be times 46, because it's, again, 1-to-1 ratio, is 5.93 grams. Oh, sorry, 94 grams, because obviously rounding properly, and it's going to be D. All right, so the main thing here is to do this quickly. Remember that carbon dioxide is 44 and ethanol is 46. They're good molar masses to remember off by heart. Question 11. The galvanic cell was set up below like this. From this, I need to know what's going on. So I need my data booklet and looking at what's going to happen here. I got iron and iron, so therefore I've got these two. So where am I? I've got this guy here and this guy here. And I've also got silver and silver. So I've got this guy here and this guy here. What that tells me is my silver is going to be my cathode and it's going to be reduced. So this is my cathode, it's going to be reduced, and I'm going to have silver ions going to silver solid. And therefore this one is going to be my anode, which is going to be my Fe2 positive going, no, other way around, Fe solid going to Fe2 positive. Because I know that, this thing here is going to react with this thing here. This thing here is reacting with this thing. The strongest oxidant, top left, is going to react with my strongest reductant, bottom right. So now I know what's happening. What is going to happen? A gas forms at the silver electrode. That's not going to happen. The mass of the silver electrode increases. Well, I'm making silver solid here, so that looks pretty good. Silver ions move towards that electrode. They cannot do that. That's just not possible. They're separate. It's never going to happen. Electrons move from my silver to my Fe. No, that's not going to happen because electrons are actually going to be going towards the cathode. Remember, in galvanic cells, electrons always flow towards the cathode. So B is our correct answer. Let's move on to question 12. The overall reaction for an acidic fuel cell is shown below. So therefore, that's our acidic fuel cell. Notice that the fuel cell is this is a common reaction for fuel cells. Basically the combustion of hydrogen is my reaction for my overall one. Porous electrodes. Porous electrodes are often used in acidic fuel cells because of why? A, they are highly reactive. Well, that's not true. Things that are reactive are my fuel and my oxygen. My electrodes should not be reactive. If they were reactive, they'll need to constantly be replaced. We don't want that to happen. Cheap to produce and readily available. No, that's what makes our fuel cell so expensive, is our electrodes. Are more efficient than solid electrodes at moving charges and reactants. That looks pretty good because you know that porous means they react faster, and that creates good efficiency in terms of how these electrodes work. Provide a surface area is the reason why they're more efficient. For hydrogen and oxygen to directly react together, they're not going to directly react together. If they directly react together, our fuel cell's broken and we're not going to get electricity out of it. So the best option is C, because the porous electrodes create a larger surface area, so the rate of reaction increases. Our efficiency of this fuel cell then increases as well. So C is the right answer for question 12. Let's move on to question 13. Question 13, we've got an energy profile. Looks like it's a catalyst-based one here based on what it looks like. Represents a particular reaction. One graph represents the uncatalyzed reaction. The other one represents a catalyzed. Uncatalyzed will have a larger activation energy, so it's the solid line. And the catalyzed one will be this dotted line here as well. So what's best matches the energy profile below? So the EA for the uncatalyzed reaction. So that is going to be this distance here. And that looks like it's 90. So therefore, we're going to cross off A and C. And then I got the delta H for the catalyzed reaction, which is actually the delta H is the same regardless. And it's going to be the difference between here and here. Alrighty, so therefore that's going to be negative 50. So therefore our answer is going to be D. Pretty good one there. Basically annotating my diagram as I go along helps me a lot with that. Question 14. An equation for the complete combustion of methanol is below. The delta H for this equation would be what? Excuse me. I've got no other data here to go on, so I'm going to go to my data booklet because I know there are molar heats of combustion in here for various fuels. Let's go find that. All right. So the molar heat of combustion here for methanol is 726, so that's 726 per mole. Now it's going to be negative because delta H for a combustion reaction is negative. I can cross off these two first of all. Now I've got this one and this one. Notice here we've got 2 lots of methanol, so therefore that needs to be times by 2. So therefore it's going to be D. These molar heats here are per 1 mole. You can see here they're per mole. So therefore, if you have a reaction like this, you need to be careful to make sure you double whatever the data booklet says for this one here. So delta H equals negative 1452 kilojoules per mole, because we want per mole of this whole equation. And with the coefficient here of 2, need to double what the data booklet says. That's question 14 done. Question 15. From the following table contains a percentage composition by mass of nutritional for some common foods. All right, carbohydrates. I know I'm not going to be straight from my data booklet again for here because I've got the energy content of fuels. So energy content of food groups, human fuel. Which of the following servings has the highest energy content? So basically I want to look at this and work out how much energy is going to come from each one. So what am I going to do? I'm going to look at my percentage of all this stuff and then work out how much energy. So fats and oils are 37 per gram, and protein is 16 per gram, and 17 per gram, and carbohydrates is 16. So what I'm going to do is multiply my percentage. I'm going to pretend I have 100 grams of food. All right. If I pretend I have 100 grams of food, I can simply times my percentage by that, because in 100 grams, I would have 8 grams of fat. In 100 grams, I would have 29 grams of protein. So therefore, if I pretend I have 100 grams, I'm going to get energy per 100 grams. And then I can work out from that which of these kind of makes more sense. Alrighty, so into my calculator, I go bracket 37 times 8 and bracket plus 29 times 17 bracket. That should give me 789 per 100 grams. Next one, I've got 50 times 16 plus bracket 4 times 37 bracket plus 8 times 17 bracket. So a fair bit of calculation here, but worth it in the long run because you're going to get the right answer. Now I've got 1 times 16, so that's just 16 plus bracket 34 times 37 bracket plus bracket 25 times 17 bracket gives me 1699, and then I've got bracket 5 times 16 plus and bracket plus bracket 4 times 37 bracket plus 3 times 17 bracket equals 279. That's per 100 grams, so therefore I need to go, right, that's my answer for A. Then I need to go 1084 times 0.8. Yeah, 0.8, because I've got 180 grams. It gives me 867.2 times 0.8. Then I go 1699 times 0.4 gives me 679.6, and then I've got 279 times 2.4 0.58, because obviously I need to go up to that, and that's 719.8. So the most energy is going to come from my bread, which is B. A lot of calculation in there, but not hard, just tedious. Question 16. The silver oxide battery is rechargeable and utilises sodium hydroxide, so it's an alkaline cell. It's electrolyte. The battery is used as a backup for spacecraft if the primary energy fails. The overall equation is this: zinc going to zinc oxide and silver oxide going to silver. So therefore I can see my zinc is being oxidized. So that's going to be the anode. I can see my silver oxygen is being reduced. That's going to be the cathode. When the battery, that's when it's discharging by the looks of it. When the silver oxide battery is being recharged, so recharged, I'm going to go going backwards. The reaction at the anode, which is oxidation, is going to be what? So if I'm going backwards here, the silver is going to be oxidized to that. So it's going to be Ag forming Ag2O, and then I need to work out what's going to happen from that on. Alrighty. So actually, I don't really need to know much about that at all. It's not the zinc, it's not the zinc, it's not the silver oxide because we're going backwards. We know it's going to be A, based on the fact that we've got the silver going to the silver oxide. Because it's the anode, it's oxidation. Because it's being recharged, it's going backwards. We can see that this is being oxidized to that. A has to be our answer. And that's it.